of Dr. Giorgos Leloudas, who is a senior researcher at the National Space Institute at the Technical University of Denmark. His research focuses on the study of transient phenomena such as supernovae, tidal disruption events, gamma ray bursts, and gravitational waves. Dr. Leloudas is a graduate of the Department of Physics of the National Methodist University of Athens. He obtained actually 2 MSc degrees, one in astrophysics from the Queen Mary University of London, and one in engineering from the Technical University in Denmark. He received his PhD at the Dark Cosmology Center in Copenhagen under the supervision of Jesper Sollerman. And since he has gone through several positions, he has been a Carlsberg Fellow, he has worked at the Oscar Klein Center in Sweden, at the Experimental Astrophysics group at the Weizmann Institute of Science in Israel. And until recently, he was an assistant professor at the Dark Cosmology Center at the University of Copenhagen. He has been awarded significant research grants during his career until now, including a Swedish Research Council grant, the Willum Young Investigator grant, and he was also awarded the Koshland Prize. He has authored or co-authored more than 110 refereed publications, among which Nature papers, which have received about 10,000 citations. I don't know, there are so many things one can say. However, I'll stop here and I'll just say that in today's seminar, Giorgos will talk to us about tidal disruption events. The exact title is Tidal Disruption of Stars Around Supermassive Black Holes, from Individual Events to Samples. Dr. Leloudas, thank you very much for accepting the invitation to give us this seminar. And now the floor is yours.
Okay, hello. Thanks a lot for inviting me, and thanks a lot for this very nice introduction. For me, the special thing is what you mentioned, that it's the first time that I ever give a talk at the place where I obtained my first degree. So indeed, 19 years ago, I also finished my TDEs at the same department where you are now. So I'm really glad to be given this opportunity, even in these strange times through the internet. So let me share my screen now. Yes, and also start the presentation. Okay, let me move this because it blocks a bit my view, like this. Yes. So indeed, I'm going to talk about tidal disruption events. But first, we need to know what these are. And why these are important, right? So here is something that you might have noticed happened this year. The Nobel Prize in Physics was awarded to Roger Penrose, for predicting that black holes are a natural prediction of the general theory of relativity. And that was half the Nobel Prize, while the other half was indeed given for proving that black holes do in fact exist. And although I should note that it is interesting that even in the Nobel Prize justification, it doesn't say for the discovery of a black hole, but for the discovery of a supermassive compact object at the center of our galaxy. So people are still cautious about this, even if we think that it can be nothing else than a black hole. And how was this discovery made? These 2 independent groups have monitored the orbits of stars around Sagittarius A star, and they have found out that they can explain these orbits only by the presence of an invisible object located at the position of this star. Well, the star marks the black hole here, and this object cannot be anything else than a black hole. And not only they exist, but you can even take a picture of them. And you might all have seen this very famous picture obtained with the Event Horizon Telescope at the center of M87. And to the right, for comparison, I'm showing this very famous picture taken by the HST of M87. Now, the mass of the black hole in M87 is about 1,000 times greater than the one in the Milky Way. So we know that black holes span a very large range of masses. Now, why do we care about all this? And these are just a few reasons, right? I mean, I bet you could fill many slides with reasoning why we are interested in black holes. But some of the main arguments are that black holes are the ultimate test for general relativity, I'm sorry. And supermassive black holes are found in all, maybe this is a very strong word, but at least most galaxies, and they're linked to the galaxy formation and evolution. The way the galaxy has evolved is strongly linked to how the black hole has evolved, and this can be this is now a common. Everybody believes that in that. For example, the M sigma relation implies that this must be the case. Now, the formation history is imprinted in the basic properties of black holes, and in that respect, we're pretty lucky because black holes only have two properties, mass and spin, if we put charge aside, which is not important for astrophysical applications. Now, the thing is that we can only measure the black hole masses for very few cases. Very nearby galaxies where we can do maybe what we did for the Milky Way or some other methods, or for active galaxies through the reverberation mapping. But in reality, these do not exceed 1% of the overall galaxy population. So 99% of supermassive black holes in the centers of galaxies are invisible to us because they are quiescent. There's no way to see them. And here enter tidal disruption events. So what is a tidal disruption event? Now, to the left, you have, again, this orbit, this trajectory of this famous star S2 near the center of our galaxy and at the location of the black hole. Still, even if this goes very close to the black hole, it's quite far from the tidal radius of the black hole. The tidal radius for a given star is the radius where the tidal forces from the black hole will overcome the self-gravity of the star and will unbind the star and destroy it. This is basically what we call a tidal disruption. And already by 1988, Martin Rees showed that you expect half of the material to remain bound and half to be flown away. Now, the bound material will eventually return and form an accretion disk. And from there, it's going to be accreted by the black hole. And early studies had predicted that this will produce a luminous flare that will decay as t to the minus 5/3. This is a famous relation. It has been debated, but it's still there. And the point is that you will get a transient event when you have a tidal disruption. And this could be similar to a supernova. You know, the light curve will go up, it will brighten suddenly, and then it will go down. So TDEs will illuminate dormant black holes for a short period of time. So black holes that otherwise you would never be able to study or probe will suddenly be accessible. And it is possible, actually, through some assumptions, to relate the observations of the light curve, such as the luminosity evolution, with the fallback rate, and even predict the mass of the black hole, the mass of the star that was disrupted, and basically its structure. Of course, this involves a lot of assumptions because it's a model that depends on many parameters. And but it has been shown that actually it is a fairly accurate method of measuring the black hole masses. So, for example, if you, for these TDEs that you see there, the prediction of the black hole mass through this method by studying the TDE is not very different than is within 1 sigma from other methods, such as the M sigma relation or the bulge black hole mass relation, etc., that you can obtain differently. This means that if in the future you study enough tidal disruption events through LSST, for example, that will find thousands, you will be able to study to measure black holes of galaxies that would otherwise be inaccessible. In certain circumstances, it's even possible to constrain the spin of a black hole. And this was from a paper we wrote back in 2016 about a very special tidal disruption event. I'll speak a bit about this later, but that's not the topic of today's talk. But the point is that under some circumstances, if the mass of the black hole is very high, you expect the tidal disruption to happen inside the event horizon, so it would be invisible to our eyes. But in order to avoid this and to see the tidal disruption, you need the star to be spinning rapidly. So here, for example, the gray area indicates the constraints we have on the mass of the black hole, while then if you assume a different mass for the disrupted star, you end up with several allowed regions for the spin parameter. So for example, for one solar mass star, you would have to have a black hole that's spinning above 0.7 of the maximum. Never mind. Let's go back to the general introduction. So have tidal disruption events actually been observed? Because, you know, a few years ago, you might not be certain about that. But we think so, yes. Now we have a number of good candidates in many different wavelengths. You will hear me use the term thermal and non-thermal. I'll get back to this later. But the first discoveries were made by Rosat in the X-rays, and they're mostly sparse data from different events. And they kind of fit the picture of black holes. They have the correct temperature, the correct luminosity. They were found in the X-rays. And they even, if you put them all together here, could maybe follow this famous T to the minus 5/3 law. But of course, there's not much else in this data. And it can be debated whether it could be something else when you have so sparse data. Then came the UV through GALEX. GALEX was a satellite that was surveying the sky, and it also caught these events that are believed to be tidal disruption. Again, these were found in archival data. So even if these were TDEs, people were not able to go there and study them at on the spot and verify this. So they still remain candidates. And we've also found TDE candidates in the gamma rays. So the Swift satellite has found at least 3 TDEs that we term as jetted or relativistic, as opposed to the thermal ones that I'm mostly going to talk about in this talk. The most famous of those is this event Swift J1644 plus 57. And these events show very strong variability in the X-rays. They're also detected in the radio, and it's compatible with synchrotron radiation. And then finally came the optical. The first optical TDE that was a very good candidate was a famous event, PS110JH, and it was discovered by Pan-STARRS. Pan-STARRS was a rolling transient survey, and at the time they were able to also obtain spectra and have multi-band light curves, and in general this object fit the picture of being a tidal disruption. First of all, it was in the nucleus of a galaxy, which is number one, let's say, a criterion to be classified as a TDE. So in general, it fit the predictions, but there was also a big surprise. The spectrum that you can see here did not show any hydrogen at the location of H alpha. This is the rest frame wavelength. Very few objects, as you know, do not have hydrogen in their spectrum. Instead, there was this strong helium-2 in 2 lines. And this created a very interesting debate at the time, whether this tidal disruption event was due to a helium star, so a star that didn't have hydrogen in the first place, or whether this could be due to radiative transfer, some physics. And you know, like the possibility of having a helium star would be very low. So I think now we are certain that it had to do with the physics. I'll go back to that. Now I'll skip a few years, and I'll come to the point. I'm now at 2020, which is the point where we have a class of optical UV TDs. And this is from a recent review by Van Velsen et al. That has collected the observations of about 35 events we're now up to. This is why I put the table there. It's not for you to look at the coordinates or any numbers, but to appreciate what is the status of the field right now. We have about now 35 events. We're at the stage where each one individually is interesting, but we're at the stage also where we're studying now samples. And there's indeed some events that could form a class, and they are the best candidates for thermal TDs. First of all, they need to be nuclear. They need to be at the nucleus of a galaxy. And then they have some photometric criteria that they all obey. In particular, if you measure their temperature, their color temperature, it seems to be rather constant, which is not the case for a supernova. Supernova being the main contaminant for any kind of transient. Supernova are explosions of stars, and you have an expanding photosphere that cools. So you expect and you see the temperature to go down with time. This is not what you see for tidal disruption events. And there's also some appreciable diversity in this class. Concerning the spectra that I'm going to talk a bit about today, and the dominant picture that was already in place in 2014 and that dominated for a few years was that TDEs span a series from helium to hydrogen-rich emission line events. So you see here on the top of the graph, you have events that had strong helium-2, sometimes blue shifted, while there was no visible H alpha. This was the same event that I showed you before. And then you have some maybe intermediate events, and in the end you have some where H alpha is the most dominant line. And indeed, this was the picture, but I will show that it's more complicated than this. Now, a couple of problems with the thermal TDEs. Thermal are these optical UV TDEs, right? In contrast to these relativistic jetted TDEs that Swift has discovered. These are discovered by optical surveys, and now they by far outnumber the other ones. Despite the fact that, so, I mean, the main problem is they should not exist, right? I mean, accretion around a black hole should be expected to produce X-rays, and therefore X-rays is the natural wavelength where we would expect to see them. But we see them in the optical, so what's wrong? And only a few of them are detected in the X-rays, as you can see from this collection of data below. So the main question is, what powers the optical luminosity and where do the X-rays go? Now, there are today two main competing scenarios about this. The one is that you have some sort of reprocessing photosphere that reprocesses the X-rays basically to optical UV radiation. So, for example, in this picture to the left, that beyond showing the reprocessing layer, maybe you can see that there's some outflows here. And it also serves as a sort of unification scheme, not very different than the one that we have in active galactic nuclei, where you have a super Eddington accretion disk, and you have outflows that create some sort of photosphere. And this is where X-rays get reprocessed in the optical and UV. And in fact, you will have even a viewing angle dependence, in the sense that if you look here, there will be less atmosphere, less photosphere, and you are more likely to see X-rays from a TDE. And if you look exactly through the pole, you might see the jet. While the majority of the thermal TDEs are observed from these sort of angles, so very few X-rays get through. But there's also a sort of competing model. It's another view that says that what we're actually seeing is not actually the accretion, is the circularization of the material, is the formation of the accretion disk, the phase before the accretion. So the star has been disrupted and destroyed, and while the debris circularizes, so it forms this accretion disk, you have the formation of shocks between debris streams that create the luminosity that we're observing. And this is actually a hot debate in the TDE field. What of the two is happening? Now, let's speak a bit about my research and how, first of all, I got involved in tidal disruption events in the first place. This happened in 2016, when there was this event, Assassin 15LH, that some people proposed to be the most luminous supernova ever. And I had been doing research on superluminous supernova myself, and also on host galaxies on superluminous supernova. And this event did not fit the picture. You see, here you have the transient phase space of transient events, where here you have the characteristic timescales, and here the luminosity. And Assassin 15LH was found to be more luminous than superluminous supernova that are found in this area, or tidal disruption events that are found in this area that are typically more luminous than typical core collapse or thermonuclear supernova. But it was found in a host galaxy that was completely different from those of superluminous supernova. And not only this, it was found in the center of the galaxy. So, of course, this raised the first concern for it being a superluminous supernova. You can see here in this compilation, this is the main sequence of galaxies, and in gray, and the blue points are where you find superluminous supernova, so they highly start forming, while red points are where you find TDEs, so they're quiescent galaxies. So 15LH was even more quiescent than most other where you found TDEs. And on top of that, the transient event happened in the center. And it also showed this very peculiar behavior that the first people that published it as a supernova had not observed in their publication. They stopped their observations here. But after that, it showed this rebrightening in the UV that was equivalent to a reheating. So like temperature increased again and then flattened for many, many, many days. Anyway, we interpreted this as being an extreme tidal disruption event, not a normal one, around a rapidly spinning supermassive black hole for the reasons I spoke earlier. Now, I've been for many years part of this large collaboration at ESO, where we're using the NTT telescope in La Silla, and we have a large fraction of the 90 nights per year on this telescope to observe transient events. And there's several science groups, and I'm co-leading the one on tidal disruption events. And so I'm gonna show you some results that came out of this recently. And the first one will be the one about this particular tidal disruption event, but most importantly about the implications. So this was a very well observed tidal disruption event because it was discovered at pre-maximum phases by the Assassin survey with this name, Assassin 18PG, but I'll be using the names that are assigned to transients by the IAU, the International Astronomical Union. It does not have any X-rays. The temperature remains constant around 25,000 degrees. These are the light curves, UV and optical light curves from SWIFT. And we obtained the black hole mass to be around 3.3 times 10 to the 6th solar masses. Now, this paper is mostly focused about spectroscopy. We obtained a very, very rich set of spectra, both in low resolutions, as you can see to the left, but also in medium resolution with extruder, which allowed us to fit at late times to obtain the black hole mass via the M sigma relation, and even higher resolution with UVs. And what I would like you to look at is the first spectra first, where the locations of H alpha, H beta, and H gamma have been marked. Let's look at this spectrum first, okay? Now, here is the location of H delta. And there's something weird here. I mean, previously this line had been identified as H delta, but now H delta, if you take this to face value, it's stronger than H gamma, much stronger than H gamma that is not there. It's stronger than H beta and almost as strong as H alpha. So something doesn't fit. If instead you identify this line as nitrogen 3, a whole new picture emerges. So there's two nitrogen 3 lines, the one here next to the helium 2, and another one here. And there's also the Balmer lines and helium 1 marked. And this is how this evolved with time. And I would like to stress two things. So the identification as H delta doesn't make sense. Instead, for many TDs, and not only for this one, it really makes sense to see that this line, the helium-2, what was proposed before as a helium-2 line, is a blend of helium-2 and nitrogen. And so this would be identified again as nitrogen. And this line, seen mostly at early times, can be identified with oxygen-3. So what does that mean? I remember I showed you just before a plot where people had been dividing TDEs to hydrogen-rich and helium-rich, depending on whether you had helium or hydrogen. But it seems that the picture is much more complicated than this. So we updated this graph that I showed you earlier with these green events here, of which the middle one is the one that we wrote the paper about. And it shows that, that these lines were there very often. So in particular, check this one, Assassin 14 Li is a very famous TDE, okay? It has, I don't know how many papers written about it. And it has exactly the same lines as AT 2018 DYB, exactly. And actually, because even the full width have maximum of the lines is lower, you can clearly separate, in this case, the helium-2 from the nitrogen-3 line. So, so we identified a class of nitrogen-rich tidal disruption events. And not only this, we identified that these lines were common in many, many previous archival TDEs. And where do these lines come from, nitrogen and oxygen? These come from Bowen fluorescence. Bowen fluorescence is a mechanism that is found in many astrophysical systems. So you get these emission lines in all sorts of objects, ranging from X-ray binaries, planetary nebula, Wolf-Rayet stars. They have even been suggested for AGN, but only been identified recently in maybe 1 or 3 or 4 now objects. Anyway, the idea is that you need photons that are in the extreme UV, shorter wavelength than 230 angstrom or so, and these ionize helium to helium-2. When helium-2 recombines, you have, except the lines on the optical, you have dominantly the helium-2 H-alpha line at 304 angstrom. 300, yes, and at this wavelength, there happens to be some transition of oxygen-3 that are almost at the same wavelength. So every time the helium-2 recombines through Lyman alpha photon, this can excite these oxygen-3 lines, which again, through a cascade, excite some nitrogen-3 lines, and these can return to the ground state through several transitions, including the ones in the optical that we saw in the spectra of these TDE and of the other astrophysical phenomena. So we have found this mechanism in TDEs and shown that this is the case for many events. What are the implications for this? So I told you before that this thermal TDE had a temperature measured through the UV and optical luminosity of 25,000 Kelvin. Now, this temperature is not enough, is orders of magnitude below what is needed to provide the Bowen line, to power the Bowen lines. So because you have very, very little energy below in the extreme UV, and these lines need extreme UV or X-rays to be powered. So the implication is that since you see these lines, there are X-rays, but they are hidden. So as you expect in an accretion event, we do have the X-rays, but now we see them indirectly through this Bowen mechanism. It's quite difficult to explain this through the other, through the shock, I think, mechanism. Now, so I think it's a very important observation because it supports the accretion origin for tidal disruption event and the presence of a reprocessing layer. In fact, it has been proposed that the line width of TDs is not set by kinematics, as is done for supernova in some case or other phenomena, but the line width is set by electron scattering. So the more scattering a photon goes through to escape, then the more wide this line becomes. In a sense, then, the differences between this TD, this very famous TD, which has exactly the same lines as AT 2018 DYB and 2018 DYB, is there are two differences. This one has broader lines, so you see here it's even blended, while here you can clearly separate the two lines. The one has like 12,000 kilometers per second. This is around 4,000 kilometers per second, the width of the line. But this one also has X-rays. So this is consistent with the fact that you can observe the one closer to the pole, not at the jet. It's still not here, but somewhere where you can still have more X-rays to escape, while the other being closer to the plane of the disk, where you have more, it goes through more material, it goes through more scattering, and not only X-rays disappear, but because they get reprocessed, but at the same time, the width of the line gets broader. I should say that now this is kind of accepted that these TDEs that exist. So you have these Bowen-rich TDEs. And in fact, this is by another paper by Van Velzen et al., where they have actually looked and separated the properties of tidal disruption events based exactly on this idea that some of them have a different spectral appearance, and they show these Bowen lines. And I'm highlighting these two graphs that show the Bowen TDs are in green, that if you measure the black body radius of the Bowen TDEs, they're found to be systematically lower than the ones of the hydrogen TDEs. By the way, these authors claim that there are very few purely helium-rich TDEs. So most TDEs that show helium are indeed the ones that have Bowen features as well. Very few only have helium but no Bowen. And the other thing, again, is that the rise time of the light curve of a TDE seems to be much longer for the Bowen TDEs on average than the one for the hydrogen. So they suggest that this must mean that TDEs with Bowen that show the Bowen feature have to be more dense, because they have smaller radii and longer rise times. And furthermore, this implies that the rise time might not be driven by the fallback time scale, which was, of course, very important to derive the mass of the black hole, as I told you in the first introduction. But it could be just diffusion. So it takes more time for the photons to escape, and therefore the light curve rise time is longer. Now, let me see what time it is in order to see if I'm going to go through a couple of more slides. I think I'm going to, I'm going to do that very quickly. I just want to show 3 slides more about 3 more papers that we published with ePesto, highlighting just a few things on different TDEs, individual TDEs. And then I'll go back to samples. So this was another TDE that we studied with Pesto. And there we saw it demonstrated iron 2 lines, some multiplets here. So the spectral diversity increases even further. Indeed, the light curve also showed some similarities to Assassin 15LH. And let's not go more in the in the physics, but This is another TDE where spectra showed a very interesting behavior. So you see, once you start obtaining many spectra, you start seeing very interesting things that could have missed in the past, where we only have a few spectra of a few TDs. So look at this H alpha profile, for example, where in the beginning it's kind of flat top, then it develops a double horned profile, and then in the end it changes again, and finally it becomes more like a single peaked profile. And this is seen also in H beta. And we're wondering whether we're seeing directly the disk now, as you would expect. Another interesting thing is that we observe a flat Balmer decrement. So H alpha over H beta is approximately 1, which is different than what you see in AGN, or different in what you expect from case B recombination, standard case B recombination. So maybe this is due to collisional excitation. Finally, another TDE that we published recently, and is a very well observed fast event. Fast, it means, now this is becoming interesting for the TDE experts, but I want to say that there's a few TDEs that, I mean, there's around 30 TDEs and they have some certain luminosity at time scales, but there's only 2 or 3 that are fainter and faster. These are harder to detect because obviously it's easier to find something that is brighter and that evolves in long time scales than something that evolves very fast and is faint. So there's only 2 or 3 faint events, but this is interesting because the rate of the TDEs does not really match with what you were expecting, but it could be really different if we're missing most of them. Yeah, anyway, we studied this TDE in a big detail. It was detected in the radio, in the X-rays, everything. And we tried to make a consistent picture, but that's a whole other talk. I'll go back to spectroscopy now. And I'll just show you that when you have some good data like the one I had for AT 2000 TDYB, it's possible indeed to fit the spectral lines and study their behavior, such as the evolution of their width for different lines, H alpha, H beta, all the, you name the lines, ratios, line ratios, such as the Balmer decrement here, the one I already mentioned. It's also close to 1. It's also not standard case B recombination. It's close to 1. And you can also measure offsets. What are the central wavelengths, and whether this implied some kinematic offsets or not. Anyway, the point is that when I did my paper, I wanted to compare with other events, especially the ones that were nitrogen rich, and I took some data from the literature and I tried to get this data, because this data has been out for a few events, and but it's done by different people, it's done in different ways, and it's not easy to compare. So, and the first graphs that I made here show that for especially a few line ratios, for example, they are all over the place. They don't seem to point to something. There seems to be a high diversity. So, so there's a need for a systematic study, and this is what my PhD student is doing, Panos, who, by the way, also finished, obtained his degree in Athens at the same department, and he's doing a PhD now with me in Denmark. So he's studying all literature TDEs up to 2018, and he's trying to treat them homogeneously. Particularly important is to do the host subtraction and the continuum removal in a consistent and homogeneous way in order to be able to study these events. And the purpose is exactly to do to get some reliable numbers out in order to do physics. So I'm going to show, this is work in preparation, and I don't want to show too much. I'm going to show some example graphs, such as the full width have maximum evolution of H alpha for a number of events. This is the kind of things you can do. And why is this important? Well, on the left, again, you can see the H alpha to H beta ratio that I referred to for the previous two TDEs. And indeed, you can see that it's all over the place, right? I mean, you have from the standard case-B recombination ratio around 3, which is also closer to what you see in AGN, but you can also see even ratios below 1 and ratios that vary with time. And another, for example, indicator could be the helium-2 to the helium-1 ratio, because obviously this is related to the degree, to the ionization parameter, right? I mean, the more you have the gas ionized, this ratio increases. And in fact, it seems that for many events, it seems to increase with time at late times. And this is work in preparation. As a last plot I'm going to show from that is that you can also compare the H alpha luminosity, for example, with the radius of the TD obtained from the literature at different phases. And there seems to be a clear correlation here. I mean, there is a correlation in that the H alpha, the events that have the strongest H alpha are the ones where we measure a larger radius, this could really help identify the differences between these hydrogen-rich TDEs or not. This fits with the picture that has been proposed. This is, of course, don't take this too seriously in the sense that it's obviously a spherically symmetric case that cannot be true, but this is a model that had been proposed and can be generated to generate spectra with radiative transfer. That citation is missing. So I'm sorry. This is by Roth et al. That has proposed that the H alpha photosphere is outside the helium-2 photosphere, which is outside the continuum photosphere. And this could fit with this picture, right? I mean, the larger the radius, then the H alpha should be even further out and emitting strongly also because of the radius. And finally, last part of my talk, I would like just to say a few words on polarimetry, because this is something that I'm also doing. And to get this more interesting, I will let you know that spectral polarimetry provided the first evidence for the unification of Seyfert's 1 and Seyfert's 2 back in the days, right? So this is the nucleus of this event of this galaxy in total flux, but in the polarized flux you see H beta that was narrow to be broad. So this is Seifert 2 that in polarized flux appears like a Seifert 1. What does that mean? This gave the first hint that polarization comes from scattered light, right? So although we were not able to see directly the broadline region, if we see at scattered light, we see the broadline region. So this is by Antonucci and Miller, 1985, and it was one of the first evidence for unifying AGNs that in the end are not very different than TDEs. In the one case, you have gas falling in a black hole. In the other case, you have like a star falling in a black hole. Okay, there are many differences, but there are also similarities. And here there are more examples from another paper showing Seyfert's 2 in polarized flux, and H alpha, you can see that it appears broad in many cases. Now, what about supernovae? This is where I come from. So polarization in supernova usually has to do about asymmetry. If you look at this graph, it shows a spherically symmetric case, or rather a spherically symmetric projected case on the plane of the sky, and different polarizations. If it's spherically symmetric, all these polarizations will cancel out and you will see a zero net polarization. If, however, the photosphere is not spherically symmetric, then polarization will not cancel out and you will measure some net polarization. Same is the case for this case where you block some part of the photosphere because of a line forming region, for example. This again, you will observe that the continuum is polarized. And a very good example is for type 2 supernovae that come from red supergiants that have a long plateau and that have been shown to have almost zero polarization during the plateau phase, where the core is surrounded by this massive hydrogen envelope, which is almost spherically symmetric. But when the light curve falls from the plateau, which is the time where the core is revealed, you see the polarization increase, because this is the time where you actually see the center of the explosion, which actually is more asymmetric than nature does not give symmetric explosions. It also has to do with radiative transfer and the opacities. So I will skip that one. We had a paper also about the polarization of this very particular event, but I'm going to skip that one to go directly to this first sample, which is again work in preparation. You should not focus at all the panels. You should only focus at the top 2 rows and forget all the 4 bottom ones. And these 3 columns are 3 different tidal disruption events. And on the first row, you see the flux spectrum, the ordinary spectrum, the one you're used to see. And in the second row, you see polarization. And you can see that for all 3 events, it rises in the blue. And there's more polarization in the blue than in the red. We tried to interpret this with an opacity effect, but we had actually neglected the fact that the host galaxy itself contributes a lot, and it contributes more in the red than in the blue. You have to realize the TDE is a very blue event, while the host galaxy is typically a red galaxy. So the fraction of contamination in the red is very different than the fraction in the blue. So once you correct, though, for interstellar polarization and this effect, as it's been done here, you can see that for many parts where there's no spectral lines, so here, for example, or here, or here, the polarization is statistically significant with being constant. This is very important. And then you have a depolarization in the emission lines, like here, H alpha. Here you have the H alpha line, and polarization falls, it's depolarized. And here you have all these Bowen lines and the helium-2, and again, polarization falls. And you see the same here as well. And both these signatures are consistent with electron scattering as being the source of opacity. So electron scattering has no wavelength dependence. The opacity due to electron scattering has no wavelength dependence. And this is nice because it means, and again here, you have a depolarization in the lines. Here's H alpha, I'm sorry, this is not clearly said. This is focusing on the velocity profile of the H alpha lines. And you can see that and in the red, you see polarization. You can see there's a depolarization. Again, this is consistent with the fact that these peaks in particular, this peak here, 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 at the wings of the lines is consistent with the fact that they come from electron scattering. So both line and continuum polarization seem to argue that it is indeed electron scattering, as it has been proposed, that causes both polarization, but also the spectral appearance of TDEs. I think I'm going to skip this. I'm also going to skip this, except saying that with polarization, it's possible to see if a system is axially symmetric by rotating the polarization, the Stokes parameter plane, let's say, but it doesn't seem that it's completely axially symmetric. There seems to be something more than this. Most of the polarization is carried by in one axis, but there's more than this. If it was completely axially symmetric, you would see this rotated parameter to be consistent with 0, but it's not. And the fact that we're also having modeling to compare with these observations now. So stay tuned, because this is work that is going to go out soon, and we think it's very interesting. So that was it, and thanks for listening.
Thank you very much, Giorgo. And I think we have time for questions now. Okay, so you could raise your hands if you have questions, or you can type them in the chat. Calliope Dasira was saying thanks for the talk. Unfortunately, she had to leave for another meeting. Okay, so Professor Mastiadis.
Okay, first to Giorgo for your nice talk. I have one question about your, now you said in the beginning that you have many thermal and few non-thermal events. What causes this? Are we talking about the same thing, or they are different totally events? Because the physics of the two seems to be very different. One has, very few of them have gamma rays, for example, and the others you have 30 of them, you said, with lots of thermal stuff, lines and all this. So they seem to be totally divided in my mind. Also, are we talking about the same physics here, or it is something?
So one possibility is that, of course, we're not looking at exactly the same thing, but we're looking at nuclear phenomena taking place at nuclei of galaxies that are different, and maybe they don't even need to be TDEs, to be honest. I mean, they don't need to be a star that fell in. But another option, I think it's attractive, the idea, or something similar, could be indeed this unification scheme here, right? So it is possible that I don't see if you can see. I don't know if you can see my mouse. That the jetted TDEs are indeed the same object, but seen exactly through the pole where a jet might or might not form. This is another thing. You are the jet experts there. I'm not sure whether every TDE should have a jet, probably not. But additionally, in order to see the jet, you would have to be looking here. Now, of course, there should be also the radio that you could expect to see at later times or at some time, even if you're not looking through the jet. But again, the radio is weak and you would only see it for the most nearby TDs. So it doesn't really exclude this possibility, I think, yet. I mean, radio has only been seen for 1 or 2 TDs, except the relativistic ones. So one possibility is that indeed, a tidal disruption that happens to be seen by here is ending up to be like the relativistic TDs that Swift has discovered. And this could also explain why these are very rare. I mean, compared to the other ones now that we find many more numerous ones from transient optical surveys, because there's many more angles from which you would experience this as a thermal TDE than a relativistic TDE.
Okay, thank you.
Are there any other questions from the audience? Okay, till you think one, I'm going to ask my question. So again, going back to the jetted TDEs, and I was wondering if this is the case and there is this unification scenario that you're thinking of. This means that if we see a jetted TDE, most likely we are seeing through the funnel. So I was wondering, for the 3 jetted TDEs that we know of, what is their spectral classification? Do we see the Bowen lines, or are these like hydrogen rich?
Right.
Because this might have, since the Bowen lines from your talk, I understand that they are the result of X-ray reprocessing. I would expect not to be so prominent in the jet
Right.
TDEs.
Okay. It's a very natural question to ask after listening to this talk. The thing is that these three jetted TDEs are, one, at a much higher redshift than the rest of the sample. So, and second, the most famous one, where is this? Ah, here. The most famous one, J1644, is definitely very much obscured. So there's dust. And there's basically we don't see it in the optical. I mean, we have taken data, we barely see the variability because probably it's due to dust. We don't see the optical wavelengths, and therefore the only thing we see is the host galaxy. Any signature is washed away. Now about the other two, I'm not so familiar. I mean, but this was also at the lowest redshift, the lowest redshift of these three. The other two I'm not so familiar with, but they're definitely at redshift above 1. It makes it very difficult to get a good optical spectrum that would observe an event of luminosity equivalent to the thermal TDEs. You wouldn't see the spectrum. You wouldn't see the event really, and it will be buried within the host galaxy. It's technically difficult. So I don't think we have the data really.
Okay. I see one question on the chat. So Marcos is asking, Marco, would you like to ask yourself or should I read it?
You should read it.
Okay.
I'm not sure.
I can read it. And two questions. In the case of X-ray are being observed by the TDE are observationally consistent with standard disk modeling of AGN or X-ray binaries. So, and you're not talking about the relativistic TDEs, right? We're talking about the thermal TDEs where you have X-rays, I guess. So there's a small out of the 35 that I mentioned, maybe, I don't know, 8 or 7 show X-rays. And the answer is, I don't know. You see, like, depends on the audience. You get here, you come here to speak about your expertise, that is the optical UV, and everybody wants to ask about the X-rays. The answer is I don't know. Now, are different lines of heavy elements observed depending on the progenitor in falling stars? So I think that so far, most of the TDEs are consistent with low mass stars in the main sequence. So maybe 1 solar mass is the typical mass, and or even smaller or around there, right? There are different predictions for let's say supergiant stars falling on the TDE, on the black hole, but these events are not consistent with these sort of events, especially because of the time scale involved. Actually, a TDE that would be given by a supergiant star, or a giant star even, except the fact that it would be much more rare because there are fewer of these stars, would evolve in a much longer time scale. This is evolving in time scales of weeks, but the ones we're talking about would be in time scales of years. So it's again another observational class, and people are maybe now trying to see if they can find events that could fit this picture, but they haven't really been found, so I can't really answer the question. We don't know.
Okay, thank you. That answers my questions.
Okay.
Can I ask a question, Maria? Can I ask a question?
Yes, of course.
Yeah. We thank you, Giorgos, for this interesting talk. And I have perhaps naive question, because I'm not an expert in this field. Anyway, the field is so new, and I'm so old, so I could not catch it. In any case, it seems that there are similarities and difference between TDEs and AGNs.
Sure, yes.
A lot. In fact, it could be the base for understanding more of the physics of the TDEs if you put the one by the side of the other and find the differences and the similarities. I mean, in AGNs, you have gas that goes around. In TDEs, you have stars that go around something like a black hole, correct?
Yes.
Yeah, okay. You have also the torus in the AGNs. You have this gas in the TDEs. You have jets in both cases. So I was wondering if you have explored some kind of a model for TDEs similar, a model that gains from the experience we have so far
Sure.
of the AGNs. That's
So
if you really have pursued this direction of using the experience we have from the AGNs to the TDEs. And it's a new field and very promising, and you are a leader. So I would be interested to hear your reaction on that.
So it's absolutely true. You're right? I mean, it's totally correct that that these systems are similar in many ways, and we're indeed trying to gain from the experience of decades of experience in AGN, as I referred many times in my talk. So you see, I was trying to look for some, also in the spectra, but also in the spectral polarimetry, in similarities with AGNs, right? I mean, I referred, for example, to the Balmer decrement, or I referred to broad lines being seen in from different viewing angles. That's exactly the kind of thing we're trying to do. And indeed, I can see there's many people that are doing TDEs now, and half of them are from the supernova field, because these are transients that look like supernova in a sense, and there are many other people that come from the AGN field. And I think that this is exactly interesting, that it's going to give a faster progress. And I wish I knew more on AGNs myself, except of course all the things I learned during my time in Athens. But in my recent research experience, this had been out of my topic for a while, and now I'm trying to cover up with basic AGN physics again to try to apply it to TDEs. So for theoretical models, if you're talking about, I'm less familiar with, but of course people are trying to build on the AGN experience.
Mm-hmm. For example, there is the Unified Agn Model. Can you take it from there? You take it from there.
I think that the model that I showed by Jane Dye et al. Is clearly, I mean, inspired by the unification model of AGNs, right? I mean, this one.
Yeah, the Yuri and Padovani, perhaps.
This one, right? So,
right,
where it's clearly the same thing. Whether it will work or not, and whether we can indeed put all TDEs in one unified picture, we will see. But of course, it's promising.
Okay, thank you.
Are there any other questions?
Okay, maybe I have another one.
I also have one, but please go ahead.
So since Giorgos used to say you are doing optical, I have a question about your lines. When you do the modeling, do you assume that is some type of LTE in order to produce the models of the lines? Or what is under the carpet? What are the assumptions for modeling? Because these are transient events, so it's not clear to my mind how.
Yes. So that's again work that is not really done yet, to be honest. I mean, spectral modeling of TDEs is not done. That's why we're doing first. So my student, supposedly when he finishes the observational atlas of all properties, we will try to then jump on the modeling. And it's indeed a big question how we're going to do that. And we've thought of cloudy maybe, but again, the question of whether it's LTE or not is the main issue, right? So the question is, we haven't done that yet, and I don't know.
Okay, so let me ask you also, Giorgo, one more question, which might be naive. So again, going back to this idea of reprocessing, which is also inspired by AGN, let's say you have X-rays that are being reprocessed in the optical UV. Is it possible, if you had very good data, to see or to search for spectral time lags in the UV and the X-rays?
Between UV and X-rays.
If, for example, you were lucky enough to see a TDE in the very nearby galaxy, for example, and you could detect X-rays and UV, is it something that you could search for, or you could?
It could be something very interesting, yes. So in fact, I didn't show this slide because I don't want to give out too much. We think we see a time lag between the peak of the bolometric light curve and the peak of the luminosity of H alpha line. But this is again by using many events, and we don't have the golden event yet to be able to do that, and especially not with X-rays. I'm talking about bolometric derived again from optical UV.
The problem with the X-rays is that they are too faint usually. In order
the
to,
problem is,
or is it?
Like I said, very few of the events have X-rays.
Yes, because they are supposedly attenuated. So.
Yes. But let's say from the 7 or 8 that have X-rays, there are a couple that have very interesting behavior, like they show some variability, or they have some short time scale variability, but we don't have the time scales for the spectra to be equivalent to these. You see what I mean? If this is what you refer to.
Yes. Okay, thank you. Are there any other questions? I don't see any other hands or questions on the chat, so if not, then let's thank our speaker again.
Thank you very much.
Thanks for having me.
Ευχαριστούμε, Γιώργο.
Thank you, ευχαριστούμε.
Ευχαριστούμε πολύ.
Παρακαλώ. Καλή συνέχεια.
Καλές γιορτές.
Καλές γιορτές.
Επίσης.
Καλές γιορτές. Γεια σου, Γιώργο.
Γεια σας.
So see you all next Wednesday again.
No Christmas
Καλό
break.
βράδυ.
We have on the 23rd and then we have the Christmas break. Yes.
Okay.
Γεια σας, αποσυνδέομαι.
Γεια σας.
Γεια σας.
Γεια σας.